Deep underground, physicists have built enormous detectors filled with water, looking for evidence of a different kind of particle. Burrowed deep within old mines, these detectors are hiding from the constant barrage of cosmogenic muons. The signal they're looking for is faint. The particles they're looking for rarely interact. But they're not a rare species. They're anything but. 70 billion pass through each square centimeter of Earth every second, and they're coming from the sun. Hey everybody, welcome back to A Field Guide to Particle Physics, Week 3. This week we're going to be turning our attention to neutrinos. Questions that you'll be able to answer after this week's episode include: what is a neutrino and how are they related to muons and electrons? Where are they coming from and why are they so hard to measure? What is the solar neutrino problem and how was it solved? And what two big questions remain unsolved about neutrinos? But before we begin with all of these big ideas, let's start, as always, with something familiar, with neutrons. As we've alluded to in the past, neutrons by themselves are unstable. Their complicated inner workings makes it easy for them to decay. They can be stabilized when joined together with protons and other neutrons in a nucleus, but left to their own devices, a neutron will last with us for about 15 minutes. Neutrons decay by emitting an electron, converting into a proton. Thereby, electric charge is conserved. For historical reasons, this process has been called beta decay, and beta decay happens to not just neutrons, but other nuclei as well. Unlike the relatively weak alpha particle, in beta decay, the electron comes out with a serious and skin-piercing energy spectrum. Beta radiation is not to be messed with. Experimental physicists in the 1930s did what experimental physicists do. They did a detailed study of beta decays from a whole bunch of different nuclei and looked at things like charges and energy, angular momentum, and momentum. What they found was really troubling. Many of the basic laws of physics were found to be violated in beta decay. And not in the nice way, like quantum mechanics, which actually makes the physical world easier to explain and understand in some sense. Beta decay violated laws of physics in a very stark and unnatural way. Charge was conserved, but energy was not. Some of the energy just appeared to vanish into thin air, and the momentum too. And trying to account for angular momentum just made things worse. So a question went out: could quantum mechanics somehow be causing this violation of these fundamental tenets of physical law? Could energy and momentum just disappear from the universe? Like, what does that even mean? Well, a different proposal came out that seemed just as ridiculous. What if during beta decay, another particle was emitted? A small, massless, neutral particle. That particle could easily carry away all of the missing energy and momentum and angular momentum, could account for all of the laws of physics that were broken, but it would be undetectable. Without an electric charge, without a mass, it's really hard to measure it. So the downside of that argument is you preserve all the laws of physics that you know and understand, but you do so in such a way that you physically can't make a measurement. You can't make an observation. What good is a hypothesis if you can't test it? That was a theoretical puzzle. To a motivated physicist, an unobservable particle is just a poorly understood particle. The first detailed model for this ghostly particle, this neutrino, was still somewhat empirical, but it captured the essential physics quite clearly. The Fermi model allowed a neutron to decay into a proton, an electron, and a neutrino, and it also predicted the statistical spread of energies and momentum that the electron and the neutrino would carry away. Importantly, this model also afforded possibilities for neutrino detection. If you hit a proton with a neutrino, so the neutrino is captured by the proton, it will convert to a neutron and emit a anti-electron. It's very similar to beta decay. Similar characters, different dance, different initial conditions. Now, to prove that such an event happened, experimentalists would look for characteristic signals of the event. The anti-electron that was emitted would find another electron and, as antimatter does, annihilate, thus producing two 0.511 MeV photons. If the free neutron then latched on to a given nucleus of another atom, another photon would be emitted. So to be successful, the experiment would need two things. First, it would need a known nucleus that would readily absorb a neutron and emit a photon at a known energy. And second, it would need a huge flux of neutrinos. The famed Cohen-Rains experiment was performed some 32 years after the Fermi model was first proposed. By this point, it was expected that nuclear reactors, like those things in power plants, were huge emitters of neutrinos. So physicists built a big tank and filled it with cadmium chloride, put detectors all around it, and put it next to the Savannah River nuclear plant in South Carolina. You see, cadmium-108 readily accepts a neutron and emits a very high energy photon. By surrounding the whole tank with photon detectors, they could readily observe all the relevant events. So, the observation of two 0.511 MeV photons in rapid succession with another really high energy photon tells the experimenters that a neutrino was captured by a proton in the tank. When the dust settled from this and other experiments, the physics was clear. Nuclear physics does in fact involve a small, electrically neutral, really hard to measure particle, the neutrino. Our modern understanding of neutrinos is considerably more complex than the original Fermi model. For starters, there are three separate varieties of neutrinos that we're aware of, three flavors, to use a technical term. The electron has its own neutrino, and the muon does too. The muon's even larger cousin, the tau lepton, which is something that looks a lot like an electron but weighs about 3,500 times as much. The tau, yeah, it has its own neutrino as well. For clarity's sake, we'll just call them the electron neutrino, the muon neutrino, and the tau neutrino. There's also room for antineutrinos of each flavor. We've kind of been dodgy about signaling when you have a neutrino versus an antineutrino up to this point, which is kind of the culture of particle physics. You see, we're not even 100% sure yet if there's a meaningful difference between a neutrino and an antineutrino, at least experimentally. This is a subtle point, and we'll get back to it towards the end of the show and in week 5. But for now, I'll start making the distinction when we're drawing out the reactions. An interaction that involves an electron only with a neutrino, something like, beta decay, that neutrino will typically be a electron neutrino or antineutrino. The flavors of particles, in other words, tend to match. So let's get into the details. Perhaps you remember the pion. The pion was one of those original decay products. Happened when a cosmic ray smashes into a molecule in the upper atmosphere before creating those cosmic muons. So that pion, you might recall, actually is a thing that decays into a muon. A typical reaction along those lines is, say, pi minus goes to mu minus plus a anti-muon neutrino. Or if you prefer the pi plus will go to a anti-muon and a muon neutrino. So in a sense, flavor is still maintained. The pion doesn't have any flavor whatsoever, and antiparticles count as negative flavor. So minus mu flavor, plus mu flavor, plus mu flavor, minus mu flavor. Whew, okay. For a more complex example, let's consider the next reaction in that pathway where the muon decays into an electron. So as you might recall from last time, the muon decays into an electron and a pair of neutrinos. That pair of neutrinos is actually an anti-electron neutrino and a muon neutrino. So accounting for flavor, we see that a muon, mu, goes to an electron, plus an anti-electron neutrino, minus electron, and a muon neutrino, muon. Again, flavor is maintained. This conservation law is not 100% true in nature. There are some predicted kind of hypothetical interactions, the so-called flavor changing neutral currents, that are really, really, really small effects that we haven't yet observed in the lab that may cause flavors to change. We just don't have the technology to measure those kinds of things yet. So by and large, flavor is conserved, maintained, and if anything, it's a useful mnemonic for how these interactions play out. In other words, flavored neutrinos or antineutrinos are strongly tied to their lepton partners. And this relationship has led to some really confusing observations in neutrino physics. Nuclear reactors are a great known source of neutrinos. Experiments around the world have set up shop next to these little neutrino factories to get their observations of neutrinos in. The largest nuclear reactor that we can see, of course, is the sun. And for a lot of us, the sun is the dominant source of neutrinos. It sprays us with something like 70 billion particles per square centimeter per second. Of course, this is nothing like being right next to a nuclear reactor, but such a high particle flux is kind of like being bombarded by light from the sun in a way, like a giant sheet of photons. There's an important distinction between photons and neutrinos that we'll kind of get to next week. So maybe it's better to say that it's kind of like a giant sheet of rain, all these particles coming after us. In any case, it's a lot of neutrinos. To observe the neutrinos coming from the sun, experimentalists use a strategy similar to the Cohen-Rains experiment. You take a really big tank, you fill it with some known liquid, you surround it with detectors, and you count the events that you see. Since neutrinos interact very rarely, to capture solar neutrinos, you have to build a really enormous tank. More liquid means more atoms means more nuclei, and more nuclei means more opportunities for interactions. The sun's neutrinos aren't coming from beta decay. They're coming from nuclear fusion inside the core of the sun. Protons are fused together to form deuterium, or hydrogen-2. That deuterium eventually gets converted up into helium-3 by the addition of another proton, but no neutrino is emitted. That helium-3 pairs up with another helium-3 to form helium-4 and 2 protons, but again, no neutrino is emitted. Neutrinos do play a role as the star's internal fusion reactor makes bigger and bigger nuclei, but proton fusion is by far the dominant source of neutrinos coming to Earth. So those neutrinos escape the sun with a very different energy spectrum than you'd find from nuclear fission in a nuclear power plant or from nuclear beta decay. It's just a different type of reaction, which is awesome because that lets us understand the physics that's happening inside of the sun without actually having to be there. What an incredible gift neutrinos are. Because neutrinos don't interact very easily, this massive shower of electrically neutral particles just flies right through us, right through the Earth, right through everything rather easily. And here comes the trouble with cosmic muons. Cosmic muons, too, are really high energy and don't really radiate, so they can fly through a lot of stuff as well. They can fly through us, through buildings, through glass, through rocks, straight through the walls of a neutrino detector. The Cherenkov radiation emitted by muons of cosmic origin flying through a detector would totally drown out the signal, the faint signal of the neutrinos coming in through that detector. To shield themselves from those cosmogenic muons, physicists have built their laboratories, their neutrino detectors, deep, deep underground. Many old mines that are very deep underground have been repurposed for physics experimental laboratories. The Gran Sasso mine in Italy, the Homestake Mine in South Dakota, the Sudbury Neutrino Observatory in the Sudbury Mine in Ontario, the Mozumi Mine in Japan are all great examples. Thousands of feet of rock then shield these detectors from the cosmogenic muons and their associated Cherenkov radiation without unduly impeding the ghostly neutrinos. So the first definitive Homestake gold mine in South Dakota. It was 5,000 feet underground, and to detect the neutrinos, they built a 100,000 gallon container surrounded by rock. They filled it up with tetrachloroethylene, dry cleaning fluid. That fluid is high in chlorine, and so it would capture the neutrinos just as in the Cohen-Rains experiment. So here the nucleus of chlorine-37 would absorb a neutrino and be converted into argon-37 by converting a neutron into a proton. The argon gas, a noble gas, would then kind of float up to the top of the detector and could be collected and effectively measured, giving a count of the number of neutrinos that were detected. This experiment ran continuously for decades. The half-life of argon-37 before decaying back to chlorine-37 is about 35 days. So every 3 weeks, they would empty the tank, count how much argon they have, see how much neutrinos they observed, and start the experiment over again. The number of neutrinos counted by this experiment, week after week after week, was pretty self-consistent. But what was shocking is that number disagreed markedly with the theoretical predictions. Every few weeks, when they emptied the tank, the measurement was the same. 1/3 of the expected neutrinos were found, which means that 2/3 of the neutrinos were missing. So either something was very wrong with the model of the sun and how it produces its neutrinos, or something else was not understood. Something weird was afoot. As it turns out, the discrepancy of observations with solar neutrinos had a lot to do with neutrino flavor. Designed to measure the production of argon-37, the Homestake Mine experiment was sensitive only to electron neutrinos. Any other flavor of neutrinos was not observed by that experiment. And as you recall, the dominant source of neutrinos coming from the sun was expected to be electron neutrinos, so it wasn't thought that this was going to be a problem at all. Part of the assumption baked in here is that neutrinos are fixed in flavor, and that made sense when folks thought that neutrinos were massless, because unlike, say, the muon, which could decay into an electron because the electron had less mass, the muon neutrino and the electron neutrino had the same mass. It was 0. So there was no way that any kind of decay would happen. There's no way that a muon neutrino would turn into an electron neutrino in some capacity. At least that's what was thought. Neutrino flavor, in other words, was thought to be strongly conserved. Of course, subsequent studies of the gnarly, nitty-gritty details of neutrino interactions revealed that no, actually, when neutrinos pass through matter, it's quite possible that they can change flavor. And moreover, if neutrinos in fact did have a mass, however tiny but non-zero, they could spontaneously change flavor as well. Especially if they move through matter, like the sun or the earth. Now, this mixing effect, especially related to mass, is quite detail intensive, and it's not even really easy to explain what a neutrino mass is. There's just so many details flying around. In any case, neutrinos can change flavor, as it turns out, and this whole business of neutrinos spontaneously changing flavor brings us to our third big insight of quantum mechanics. Given a choice, A or B, the answer only really matters when you observe it. Loosely applied to the study of neutrinos, this means that given the fact that neutrinos can transform from one flavor to another, if you happen to have a neutrino that you're observing, is it an electron neutrino, a muon neutrino, or a tau neutrino? You don't know until you do observe it. It could be any of them, actually. Now, why this applies to neutrinos and not other particles like muons, tau, or the electron has a lot to do with the fact that the neutrino masses are really, really, really small, and also that neutrinos actually don't want to be branded by their flavor. Just as magnetic north and true north on a compass are slightly misaligned, flavored neutrinos and true neutrinos are not exactly the same thing. You see, true neutrinos, things we'll call neutrino 1, 2, and 3, are actually the real particles. They're the neutrinos that actually have small but non-zero masses. They're the things that move from point to point. But the thing that interacts with other particles, say electrons or muons, are the flavored neutrinos. So an admixture of those true neutrinos. The same thing is true for muon neutrinos and tau neutrinos. They're just a useful representation, a useful mixture of the two. Now, this can really only happen because of quantum mechanics. Now, if this feels dizzyingly complicated to you, don't worry. It really, really is. It's crazy. Next time any physicist comes to you and tries to explain that the laws of nature are beautiful in some capacity, just ask them about neutrino masses and laugh in their face. It's horrible. Anyway, here's the big takeaway. Neutrinos that are born in the core of the sun are born as electron neutrinos. Now, this is a quantum admixture of neutrino 1, 2, and 3. And as these neutrinos move through the sun, through space, and through the Earth to the detector, that quantum admixture, that percentage of 1, 2, and 3, gets shuffled around and tends to change. That shuffling depends on the masses of neutrinos 1, 2, and 3, and in space it's a really slow process, and neutrinos are a really fast particle. They get from the sun to the Earth in something like 8 or 9 minutes. For a long time, folks just assumed that it wouldn't matter, which turned out to be a bad assumption. As it turns out, propagation of neutrinos through matter is a lot different than the propagation of neutrinos through space. Wolfstein first showed us how, as neutrinos propagate through matter, they're moving through a whole bunch of electrons and protons and neutrons and a bunch of other stuff, how that can actually impact the neutrinos and cause them to oscillate between different flavors. The idea is that the relationship between the true neutrino states, 1, 2, and 3, and the kind of flavored neutrinos, that misalignment, if you will, actually depends very strongly on the matter through which the neutrinos are moving. Mikheyev and Smirnov actually improved this studies to show that, hey, this effect can matter a lot, like significantly. Indeed, their results, when applied to neutrinos moving through something as massive and enormous as the sun, means that the missing 2/3 of the neutrinos observed at the Homestake Mine experiment and subsequently other neutrino experiments was to be expected. Those electron neutrinos were transforming into muon neutrinos and tau neutrinos. And that fact was finally and precisely observed and published in 2001 by the Sudbury Neutrino Observatory in Sudbury, Ontario. Proposed as a ghost to solve a riddle with beta decay, pulling on the thread of neutrinos has resulted in a remarkable complexity that we're still unraveling today. These particles are everywhere. They're really hard to pin down, and when we finally did, it only broadened the scope of our ignorance. The solar neutrino problem was solved by realizing that neutrinos of one flavor can spontaneously change into another flavor. In other words, they oscillate between flavors. This implies that they have a tiny, non-vanishing mass. The masses are really small, and that's pretty much all we know. We don't have a handle on what those masses are. We don't even know if neutrinos have a meaningful sense of an antiparticle partner. There is a lot of work that's left to be done, both theoretically and experimentally. But the one thing that is for sure is that neutrinos are really a complicated, messy endeavor. Next time, we'll step back from all of this crazy technical discussions and visit a particle that's considerably cleaner by comparison. They are intimately related with quantum mechanics, the birth of the universe, and indeed, all of the particle physics that we've been discussing to date. These are particles that you are guaranteed to see on any outing outdoors at all. Literally, the photon.